Podcast number 3 in a series of 4 IB Physics Unit 8. This is focusing on renewable. We're looking at hydroelectric power, wind power, ocean wave power, and solar energy. There are other energy sources, but these are the ones that the IB want us to focus on. So all of these sources really have their roots embedded in solar energy. Hydroelectric requires the sun to evaporate the ocean water and to dump it at high ground so that we can have a flow downhill. Wind is due to temperature variations, pressure variations, which is thanks to the solar energy differences, different parts of the globe. And wave energy is all thanks to the wind. And of course, solar energy is down to the sun. These two charts here show that our use of renewable energy sources is increasing. The left graph shows wind power up to a predicted value here in 2010, and the right one shows an increase in hydroelectric power production. So these sources of energy are increasing. But as we saw in an earlier podcast, the overall percentage compared to the other sources is still very small. So first of all, we're going to take a look at hydroelectric power. And there's three kinds of hydroelectric power we want to look at. The first one is water storage in lakes. So essentially, we find a suitable place, which is essentially, I guess, a river in a valley, and a dam is built so that the water builds up and forms a deep lake. The water exits the lake and falls, as we can see here, gains kinetic energy, and this kinetic energy turns a turbine, which is mechanically connected to a generator, and it produces electricity. Very straightforward. There's no heat generated, so it has the potential to be quite an efficient process. The second kind of hydroelectric power that we want to look at is tidal water storage. So in a suitable spot, a barrage or a barrier can be built with turbines, so that when the tide flows in one direction past the turbines turn and generate electricity. As the tide flows out in the other direction, we also get electricity generated. So we can get electricity generated on an incoming and an outgoing tide. The way it tends to work is that the water is captured behind the barrage to generate a tidal head, and then the gates in the barrage are opened and allow the water to flow through at a relatively fast rate. Pump storage is the third kind of hydroelectric, very similar to the first one. We have a reservoir, a lake, with a very large drop to generate the kinetic energy, which we require to turn the turbine, and electricity is generated in the typical way. The interesting thing about this is that when it's normally used when there's a high demand for power, and it can be switched on straight away. We can just throw a switch and get the electricity. On a low demand period, when possibly there's a surplus of electricity being produced by the thermal power stations, we reverse the generator and we turn it into an electrical pump, and we pump the water back up. So it's acting like a battery in a way, and it's a reserve of instantly available electricity for peak demands, such as Super Bowl or something like that, when everyone's watching their television or using electrical appliances. So the water can be pumped back up. We don't have to wait for the rain to fill the reservoir. So the typical energy transformations in the first type, solar energy is used to evaporate the water. The water then has gravitational potential energy. This is converted into kinetic energy as it flows, kinetic energy of the spinning turbine, and finally electrical energy of the generator. Some advantages of hydroelectric power are that once the dam and the hardware is built, which is an expensive process, the fuel is of course free, so the running costs are relatively low. But it does rely on the presence of water, and droughts can cause shortages in electricity. Let's take a look at wind power. So wind power, it's also a flowing fluid. Hydroelectric is a flowing fluid. Wind power relies on a flowing fluid, in this case air. The kinetic energy of the air is taken and some of it is passed on to the blades. The blades are connected to a generator which generates electricity. So the model here, which we can see, the picture shows a standard 3-blade horizontal axis machine. So we need to be able to determine the maximum power available from the wind. Maximum power meaning if we took out all of the kinetic energy of the air, which is not possible. We can take a portion of the kinetic energy of the air. If we took all of the kinetic energy of the air would stop at the blades, which would cause a buildup. I mean, it just would not make sense. We take some of the energy out of a flow, similar in a way to thermodynamics and heat engines. We have a flow of heat through a system and we take some of the heat out and convert it into mechanical energy. Same with hydroelectric, we have a flow of water and we take some of the kinetic energy of the water. But at any rate, we're going to work out the maximum power available based on the kinetic energy of the wind coming in. So let's see what we've got. We have the area swept out by the blades, A. We have the speed of the wind, V, air density, rho. So we can think of this cylinder as the air which is flowing into the blades. Now, kinetic energy of the air is going to be given by half mv squared, and the power, energy over unit time, is going to be kinetic energy of the air divided by unit time. So the equation is half mv squared over unit time. So we need next to work out the mass of the air which is reaching the turbine per unit time. Mass per unit time, mass is density times volume. So mass per unit time is density times volume over unit time. But volume over unit time is area times velocity. If we go back to the previous slide, area times velocity, velocity in meters per second, is going to give us the volume of this cylinder every second that it's going through the blades. So we have mass per unit time is density times area times the velocity of the air. So let's substitute this back into the power available equation, and we have power equals half mass, which is now rho AV, half rho AV times V squared. So we end up with V cubed. So the maximum power available is half times the density times the area swept out by the blades times the velocity of the air cubed. So let's do a calculation. So let's imagine a wind turbine has a blade diameter of 50 meters. First question, calculate the maximum power available from the wind when it is blowing at 12 meters per second. So we have the equation. Power equals half rho AV cubed, which gives us half times the density of air, which is 1.3 kilograms per meter cubed, times the area swept out by the blades, which is the area of a circle, which is pi r squared. So times pi multiplied by the radius, which is going to be 25, squared, multiplied by the velocity of the air cubed, which is 12 cubed. So let's see what that gives us. So it gives us 2.2 megawatts. And that's the maximum power available. We can't possibly take that much power out of the wind because that represents the whole kinetic energy of the wind. Let's look at part 2. If each turbine takes 50% of this energy and turns it into electricity, how many turbines will we need to produce 500 megawatts? So 50%, firstly, so 50% of 2.2 megawatts is 1.1 watts. And all we need to do now is divide that into 500, and we have the number of turbines we need. So 500 divided by 1. Gives us a huge 450 turbines. 500 megawatts, a typical output of a thermal coal-fired power station. Discuss why such a power station might be unpopular to people living nearby. Well, 450 turbines, that's a lot of turbines. They need a lot of space. They're actually quite noisy. So there are some reasons why people might actually not like those. They also do cause animal deaths. Bird strikes are not uncommon, especially big birds like raptors. Next, let's take a look at wave power, ocean waves. So a common device for extracting energy from ocean waves is an oscillating water column. So this is a cross-section of such a device, and we have the waves coming in from the left, so the water is going up and down. This causes the water in the column to oscillate and go up and down as well. And there is air above that, which alternately blows out through a turbine and is sucked back in through a turbine. So we have a turbine here connected to a generator which creates electrical energy as the air is forced out and as the air is sucked back in. So that's one type. It's not the only type, but it's the type the IB wants us to be most familiar with. We also have other ways. We've got these floating barriers. We've got these devices which are underneath the water which go backwards and forwards as the waves come past. These devices go up and down as the waves come past. This first device here is very similar to this one, where they flap backwards and forwards as the waves come past. So how much energy is available from a wave? And the IB wants us to be able to quantify the power available from a wave. So to do that, we're going to make a couple of simplifications. And the first simplification we're going to make is we're going to look at this profile of the wave, and we can see it's roughly sort of triangular. And we're going to simplify it to this rectangular shape. We're imagining that this rectangular shape has gravitational potential energy above the base of the waves, the trough of the waves. Okay. We can see that the length of this rectangular shape is the wavelength of the waves, and we can see that the height of this rectangular shape is the wave amplitude. So this line here would be the mean position of the wave, up to here would be the amplitude, and again down to here would be the amplitude. So we have this rectangular shape, which is roughly equal to the same shape or the same area as the wave, with a length equal to the wavelength and a height equal to the amplitude. So the gravitational potential energy of that shape is given by mgh, and we want to work that through. So let's have a look. So the mass of the water per unit length of the wave would be given by the volume times the density, and we're talking about per unit length now. So we've got the length here. We're imagining a wave which is a meter wide. So we've got the mass is equal to the area of the amplitude times the wavelength. That gives us the cross-sectional area multiplied by the density. So that's the volume of a 1 meter length wave multiplied by the density to give us the mass. Now the height of the wave, we want to work out mgh, so we want to think about h. The height of the wave is best considered as half of this value. The center of mass is right in here, and we can think of the average height of that block being at the center of mass. So half of it is above, half of it is below. So the height is the amplitude divided by 2. So from mgh, we've got m, which is a lambda rho, times g, times h, which we've just decided is the amplitude over 2. Okay, so we're going to simplify that. We've got wavelength times density times gravitational field strength, amplitude squared over 2. But this is the gravitational potential energy of the wave. Power is the energy available per unit time, and the time is going to be the wave period. So we're going to divide that whole thing by t. Final thing, we have lambda over t is the wave speed, and that's from v equals f lambda, or v equals lambda over t. So we can remove lambda over t and substitute in v. So we end up with the wave power being the density of the water times the speed of the wave, gravitational field strength, amplitude squared divided by 2. So let's do another calculation. Waves roll onto ocean beach at a rate of 5 per minute, and they have an amplitude of 1.5 meters and a wavelength of 20 meters. Firstly, calculate the frequency and speed of the wave. So the frequency is already given as 5 per minute, but we want it per second, so 5 per 60 seconds. So the frequency is going to be 0.83 hertz. The wave speed is given by V equals F lambda. So we have 0.83 multiplied by 20, which gives us 1.67 meters per second. Next question, the power delivered per unit length of the wave. So we have our equation from the previous page, which is rho Vg a squared over 2. Rho Vg a squared over 2. So plugging the numbers in here, density of water, we need to know, is 1,000 kilograms per meter cubed. We have the speed of the wave, 1.67. Gravitational field strength, 9.81. Amplitude squared, the amplitude is 1.5 meters, so 1.5 squared, all over 2, which gives us 11.8 kilowatts. 11.8 kilowatts. If it was 50% efficient, if the system was 50% efficient and you wanted 200 megawatts of power, how long would your device need to be? Well, we know that this is the power per unit length, per 1 meter. We're going to assume 50% efficiency, so firstly we need to divide our 11.8 kilowatts by 2, because it's 50% efficient, and then we need to divide this into 200 megawatts to actually find out how long our device would need to be in meters. So let's do that. So this is 5.9 kilowatts. Now we're dividing that into 200 megawatts. So 200 megawatts divided by 5.9 kilowatts equals 33900 meters, which is not far short of 34 kilometers. So quite a large structure to generate a sizable amount of power. But these devices could be spread around a large area and not all concentrated in one spot, so it's not impossible. And finally, we're looking at solar power. So two kinds of solar power we want to look at. That is photovoltaic cells, or solar PV, and solar thermal. So solar PV, typically solar panels, the sun's rays fall on the solar panels and that's converted directly into electricity. It's a semiconductor machine. The IB doesn't want us to go into the details of how it's actually done, but just know that we have a direct conversion into electricity. Even though there's a direct conversion from solar energy into electrical energy, the efficiency of solar panels is still relatively low, but technology is improving in that, and it's now somewhere between 10 and 15% efficient. Solar thermal is another way we harness the sun's energies, and it's essentially just converting the sun's rays into heat energy of some fluid normally. This can be done on a small scale, just like heating water for a house. But this picture here shows a large-scale system. We have mirrors all focusing on a central spot, which gets really, really hot. So this contains a fluid which gets very hot, and the heat from that is transferred in a heat transfer system, not dissimilar to the nuclear power system. And then that steam which is generated can turn turbines and generate electricity. So the success of these systems, of course, depends on how much solar energy we actually get, and that varies across the surface of the Earth with the time of day. Of course, we don't get any sun at night. It varies with the seasons due to the tilt of the Earth that these diagrams show here. During the northern summer months, areas above the equator, or more specifically above the Tropic of Cancer, are going to get more energy, more solar energy, and more direct energy than places in the southern hemisphere. In the northern winter, places above the Tropic of Cancer are going to be getting less energy because the sun's rays are much lower in the sky. They're diluted because they have to pass through more atmosphere as well. We can also see from this diagram that the day length is shorter, so all these things compound to make solar energy much less viable in places which are well above or below the tropics. The greatest solar intensity is found at the tropics, between the tropics, where the sun is nearly overhead. And obviously weather patterns have a big effect on things as well. Dry areas are going to have a lot more solar intensity, so would be much better locations for solar power stations. Some places in Southern California, in the desert areas, have these places installed, and they have a lot of solar energy there. Places with a lot of rain, clouds, humid places, it's possibly not going to be a good solution. So in the next podcast, we're going to look at climate change, global warming, and the effects that the sun actually has on our climate, and possibly some of the problems that we are creating by using certain energy sources.